Okay, we have a small part remaining for today that connects the definition 2 and 3 with the definition 1. The definition 1, I've rewritten it here on the left, top left part of the board. So this is what we want to have. This is our goal, to have the convergence property from our numerical scheme. And this is what we can check, actually. Let's discuss how we check this guy. First one, here. Can you recall how we did it for explicit Euler method? How did we check a quantity like this for the explicit Euler method? What did we do? This L capital shouldn't frighten you. It's just an algorithm that you already know. It is just the formula yn plus 1 is equal to yn plus tau multiplied by fn. And that's it. This formula sits here. Okay. Here we say that we substitute an exact solution into this formula. We substitute an exact solution there. Okay. So what we did was we calculated the Taylor expansion of the exact solution, and we compared the result of our algorithm application to the Taylor expansion of the exact solution, and we found what terms were represented exactly, what terms in the expansion were exactly represented by our algorithm, and what terms remained to be the error. Don't remember. So Taylor expansion of the exact solution was at time tn plus tau. This is what we did. Plus, tell me what is next. Tn by tau, right? Right. Plus 1/2 tn tau squared plus and so on. And this so on and so on. It's enough because tau squared is already not represented by the explicit Euler. The explicit Euler expression, this is the counterpart of the exact solution computed at point tn plus 1. This is the counterpart of this, right? On the left. And in the Euler method, it is what? It is tau multiplied by fn. Well, let us say tn u yn. And this guy is who? According to the original equation, this guy is exactly f of tn un. It's important. Of tn un, and here yn. When we derived the explicit Euler method, we used an assumption. We assumed that yn is exactly equal to u at tn. We assumed that at the previous time point we exactly computed the solution. That's what we did. So you see that this is exactly, these two terms are exactly represented by our Euler method. And all the remaining part is an error. This is how we got this expression. Because what we need to do when we compute this norm is we actually, this norm. This is how we got this expression. I'm sorry, I'm misleading you a little bit now. For the Euler method, it was easy to directly check this guy, right? But if we wanted to check this guy for the Euler method, what we had to do? Very similar thing. We had to just transfer this and this to the left hand side and divide by tau. And on the right we would have f of Tn yn, right? While for the original solution, for the correct solution, we had y Tn plus 1 minus y just a second. So yes, of Tn by tau, and then comes f of Tn un plus O of t to the first power, because we divided by tau. Okay? And this says that the Euler method has the first order approximation order of approximation. So on the left hand side we have an approximation of the derivative. And this is the approximation of the original equation. So we are not having this term in our scheme. Then we and by checking that, we prove that this equation holds true with p equal to 1. This is how to practically check the definition 2. Okay, so it's possible to check the definition 2. Checking the definition 3, this property that defined in 3, is significantly more complicated. And it is only solved well for linear problems. For nonlinear problems, stability can be checked for some particular cases, but not in the general case. And there is a separate discussion about the stability, but well, it's still possible to evaluate stability of the method, but it's more complicated. So it is possible to check before solving with the method L tau. So what? It's possible to check, but it doesn't say that these two properties will give us this property. We need some theorem that connects these two properties to this property, and this is the theorem. Theorem by Peter Lax and Victor Solomonovich Ryabenkiy. They invented this fact independently, approximately at the same time, but all the materials on both sides of the ocean were under secret, under secret. So it's not possible to exactly say who invented this theorem earlier. If the numerical scheme 2 stars approximates the problem 1 star on its solution, and if 2 stars is stable, then then the approximate solution y tau converges to the exact solution when tau tends to 0. And moreover, the following inequality is true. Well, I should repeat the inequality, I just say it by words. The approximate solution, if the numerical scheme approximates the problem star with solution with order P, and if it's stable, then the approximate solution tends to the exact solution at the order P. Is it clear what the theorem states? So if we could prove this property and could check this property, we can be sure that our approximate solution will tend to the exact solution. It's very important to keep this, all these things in mind when we solve real problems, because it's very easy to get the situation when you think that you approximated the problem, or you think that the approximate solution should tend, but you did not check it. And in fact, especially this guy, most of the times this guy is responsible for the lack of convergence of the approximate solutions to the exact solution. Stability of the method is very important. So, how we prove this? It's not actually a detailed proof, it's just a skeleton of the proof. So, approximation property. So, if the method approximates our original problem, what it means? We just formulated what it means, and it's written here. It means that the residual is bounded by this product. Some constant multiplied by time step to the power of p. Okay. And next, the stability comes. When we say that this problem, 2 stars, is stable, what it means? It means that if we take as a vector v, if we take the exact solution of this problem as a vector v, remember we had 2 problems, L tau of v tau minus f tau is equal to r small, and L tau of w tau minus f is equal to s small. And we had this relation for the stable problems. So, as a v, I'm taking y tau, exact solution of 2 stars. And as a w, I'm taking the exact solution projected to the mesh. That's what I actually want to get. Okay? And I know the method is stable. Then, this is true. C3, normal the first error vector plus normal the second error vector. Let's discuss what is the first error vector. It was called r small, this r small, right? But when we use y tau as v tau, it is the exact solution of this problem. So if I write minus here, what's going to be here? Nikita, what's going to be here on the right hand side? When y tau is the exact solution of this problem. Y tau is the exact solution. It means that if you substitute it there, it makes the equality a true, it makes this expression a true equality. So, my question is, 0. 0, guys.
Why 0?
Because y is the solution of this problem. Is the exact solution of this problem. Okay? That's why this guy is 0, because y tau is the exact solution of 2 stars. Okay? Now, let's discuss this guy. When we substitute it here, what are we getting? L tau of u tau equals f tau. But plus what? Because we discussed before that if we just substitute here, we wouldn't get 0. It's not an exact solution of the approximate problem, right? But we know something about this error. Isn't it this guy? This error is this guy. Is the residual. Okay? Nikita, do you follow? Hence, we put this guy here. Okay? And continue our inequality. Because of the first inequality. We can use it here. And continue. It is less or equal to C3, this is 0, by C1 by tau to the power of p. Guys, what did we get? Get the proof of the theorem. We just got the proof of the theorem because it says that the approximate solution, the difference between the approximate solution and the exact solution by norm is bounded by some constant multiplied by the step to the power of p. That's exactly what we wanted to prove. Okay? This is a skeleton of the real proof. Why am I saying that? Because I did not discuss in detail how to check this and how to check the stability. This is simple, relatively simple. The algorithm is discussed and we showed how to do that already on the board. This is not discussed and it's a matter of separate story. For simple methods like Euler, it's easy to do directly. For more complicated methods like the ones that we need to introduce, it's not going to be that easy. Okay, I think that's enough for today, for the theory. And